Yeah, hello friends. This is Gangadhar from Maths Ganga. In this video, I am going to introduce the concept of limits. See, in the introduction of limits, we need to know about these aspects, the general discussion about limit, and the second thing is limits are for. The third thing, the need of limit concept. Fourth one, definition of limit. And the fifth one, notation of limit. And at the end, sixth one, an example for the concept of limit. Right? See, limits are basically a very important topic of calculus. Calculus is nothing but the study of change. It plays an important role in the field of mathematics and science. And in the part of calculus, in the branch of calculus, limits are also playing a very important role. And now we are going to study that concept, limits. See, usually the general discussion is nothing but in our regular life we come across with these type of sentences. Be in your limits, an available credit limit, limited period offer. In such sentences, the word limit is already involved. If you observe these sentences, for suppose, available credit limit. In regular bank transactions, we face the sentence available credit limit. If the available credit limit is like 1 lakh rupees, you are free to use up to 1 lakh rupees, and if you transact more than that 1 lakh, additional charges are applied. This is the general meaning. And coming to the last one, limited period offer. See, an offer is there at the shop, but the offer is only for a limited period. After that period, the offer won't apply. And before that period, we have that offer. That in the sense, all these statements, all these sentences usually give an idea about the word limit. Limit is nothing but a barrier. After that barrier, before that barrier, the situation is different now. The situation changes. That barrier changes the situation. Before that barrier and after that barrier, the behavior, the tendency, the circumstances are different and the results are also different. This is the general idea of limit. The same idea is useful in mathematics, and specifically in functions. Okay, so the second, this is the general discussion of limit, and the second thing is limits are for usually functions in mathematics. Limits are for functions. Mathematically, we use the concept of limit for functions. Okay, see, what is the need of the limit concept? The third one, what is the need of the limit concept? See, the need of the limit concept is if the function changes its tendency, if the function changes its behavior before and after a particular point, to study that behavior, we use the word limit and we use the concept limit. Okay, so limit usually analyzes the tendency of a function before and after a particular point, as we discussed in the general discussion, right? Then what is the definition of the limit? Coming to the definition of the limit, as we mentioned, these limits are for functions. For suppose, if we have a function y is equals to f of x. See, f is a function from real numbers to real numbers such that y is equals to f of x is the function. In this y is equals to f of x, we usually call this x as independent variable because we have independent chances to take any value in the place of x. Based on that x, we will get the values of y, which are nothing but f of x. So we call the values of y as dependent values, and we call the variable y as dependent variable and x as independent variable. See, we learned in functions that for y is equals to f of x, there is a domain and codomain. This domain is contains the values of x, whereas codomain contains the functional values of f function. We mentioned it as f of x. See, for different values of x, we will get different functional values. If one value is x1, then its result is f of x1. x1 maps to f of x1. So like this, we learn many things in functions. Now, what is the definition of limit? See, if we change different values in the domain, we will get different values in the codomain. For suppose, at a particular point A, if the values of x are changing in the surroundings of A, if the values of that means this A acts like a barrier, and we are going to analyze the tendency or behavior of the function before that barrier as well as after that barrier. That in a sense, if x is approaching to A from either of the sides, if x is changing in very smaller surroundings of A, and in that situation if f of x changes in the smaller surroundings of L, then we say that the limit of f of x is L as x is approaching to A. So definition of limit is nothing but to analyze the behavior of the function before and after a particular point of the domain. If the variable in the domain is changing in the smaller surroundings of A, as in the same situation, if the functional values are changing in the smaller surroundings of L, then we say that L is the limit of f of x as x is changing in the range of A. See, that is usually notated as x is approaching to A from either of the sides. As x is approaching to A, f of x is approaching to L. As x is approaching to A, then f of x approaches to L, then we say that this L as the limit of f of x. This L as the limit of f of x as x approaches to A. This is the basic definition of the limit. See, coming to the need as well as the definition, if you observe, if the function changes its behavior before and after a particular point, then the concept of limit arises. If there is no change in the behavior of the function before and after that particular point, then there is actually no need to use the concept of limit. But we will use, and that usage is nothing but directly results as the functional value. If the function won't change its behavior before and after a particular point, then the concept of limit is directly equal to the functional value. If it changes its behavior, then the use of limit arises. In those situations, usually we use this definition and we will observe the behavior of the function in the surroundings of that particular point. Right? See, so as x tends to A, if f of x tends to L, x is tending to A, x is approaching to A, x is very nearer to A. If x is moving very nearer to A, then f of x also moves very nearer to L. Then in that case, we say that L as the limit of f of x as x is approaching to A. See, then coming to the notation, this definition is notated like this: limit x tends to A, f of x is equals to L is just a notation for the definition of limit. See, it explains us that as x is approaching to A in the domain, f of x is approaching to L in the codomain. That in the sense, as x is approaching to A from either of the sides, then f of x is approaching to L from either of the sides. Then L is the limit of f of x as x is approaching to A. This is just a notation of the function. See, here we need to keep in our mind that this x is approaching to A, but x is not equals to A. And f of x is also approaching to L. F of x is not equals to L. So usually the mistake what we did is limit x tends to f of x is equal to L means f of x is equals to L. It is wrong. It is a wrong thing. F of x is not equal to L. Maybe sometimes equal. But this notation explains us that f of x is approaching to L. Okay, we are not able to confirm that f of x is equals to L. This gives us an idea that f of x is in the surroundings of L. F of x is very nearer to L as x is very nearer to A. The limit won't discuss at a particular point. The limit discuss in the range of A, in the surroundings of A, if there is a very minute difference between the variable, changing variable x and with the fixed point A, and if there is a very minute difference between the functional value f of x corresponds to x and the fixed value L, then we say that L as the limit of f of x as x is approaching to A, right? So as we discussed, if the function won't change its behavior in either sides of A, then there is no use of limit actually. Okay, right? So this is just a notation for the limit. The notation is limit x tends to A, f of x is equals to L. So to get more clear idea about this, let us go with certain examples. For example, if you have a function f of x is equals to x square, and this is the domain, whereas this is the codomain. For something like minus 2, the value is 4, and minus 1, the value is something like minus 2 will move to 4, and minus 1 will move to 1. Somewhere if this is 4, minus 2 will move to this 4. Okay, and if this is 0, and it reaches to 0. And in this domain, if we change x to 2 in the surroundings of 2, if the variable x is changing and moves to 2 and from either of the sides, and if this is 1.9 and the value is approximately 1.9 square, which is nothing but 3.61. If the value is 2.1, then f of x is 4.41, the square of the 2.1. That in the sense, if x is changing in the surroundings of A, in the smaller range of A, in the smaller range of A, here A is nothing but 2 for my example, right? If x is changing in the surroundings of A, if x is approaching to 2, very nearer, then in this codomain f of x is also approaching to 4. Okay, this is okay, leave this about. F of x is also approaching to 4. So as x tends to 2 from either of the sides, f of x also approaches to 4. So limit x tends to 2, f of x is equals to 4. Limit x tends to 2, f of x is 4. Actually, in this situation, the function behavior won't change. Before the 2 and after the 2, the functional value almost approaches to 4 itself. So actually, f of 2 is 4, its functional value is 4. In this case, actually, the real use of limit is not observed. Okay, then I will go with another example. For suppose, as we discussed, limit x tends to A, f of x is equals to L, as x is approaching to A. See, already we discussed about the limit concept by taking domain and codomain. Now I am going to analyze this notation and the definition of limit graphically. Graphically, x-axis is for domain and y-axis is for codomain. See, as x is approaching to A is a point in the domain. So A is a point on x-axis. And since x is approaching to A, the value of x is running towards A, either from this side, and the value of x is running towards A, either from that side. See, corresponding to different values of x on x-axis, we have different values of f of x. Corresponding to every value on x-axis, we have a value for f of x, and by joining all those, we will get the graph of f of x. Already we learned about the graphs in the functions chapter. Now, see, somewhere on x-axis here, y-axis here we have L. See, as x is approaching to A, if the graph is like this, okay, at this A, it corresponds to this A. If the y value is L, in this case, we say that limit x tends to A, f of x is equals to L. Corresponding to this A, the y value is L. As x is approaching to A, the graph also running towards the value L of y. And as x is approaching to A from right side, again the graph is running towards the value L on y-axis. Since x is running towards A from left side and x is running towards A from right side, the graph is running towards L of y-axis. We say that limit x tends to A, f of x is equals to L. This is one of the example. And coming to another thing, the situation sometimes different. For suppose, see, this is the point A, and then see the graph will be like this. And this corresponding point is L. See, as x is running towards A from the left side, the graph is running towards L of y-axis. And as x is running towards A from right side, again the graph is running towards L of y-axis. But the function is not defined at A. See, at A, the function is not exist. But before that A, the function exists. After that A, the function exists. So x is approaching to A. In the left side of A, the limit of f of x is L. In the right side of A, the limit of f of x is L. So in this case also, we say that limit extends to A, f of x is equals to L. And I will give you another idea. For suppose, if this is A, and then the function is like this, okay, and again, the function is like this, okay, yeah, this value corresponds to L1 and this value corresponds to is L2. See, now if you observe, if x is running on x-axis towards A from right side, the graph is running towards the value L1 of y-axis. So the left side, the left hand limit of the function is L1. And if the value of x is running towards A from right side, then the graph is running towards L2 of y-axis. Then in this case, we say the limit of f of x, the behavior of f of x in the right hand side of A is approaching to L2. Okay, in this case, the left side and the right side behaviors are different. So in those cases, the real use of limit arises. And in the next video, I am going to discuss the left hand limit and right hand limit and the situations, functions where the real utility of left hand limit and right hand limit are involved. Right? So in this video, we discussed about the general discussion of limit, the need of limit. What is the need of limit actually? Limit is a barrier at a particular point of domain. Before that point and after that point, if the behavior of the function is different, if the tendency of the function changes, then to observe that tendency before and after that particular point, we use the concept of limit. And the notation of the limit is limit extends to A, f of x is equals to L. This notation explains us that if x, the domain, the variable in the domain is approaching to A, then f of x is approaching to L. This equal to is approaches to. Okay, we need to understand that this is equals to is not a general equals to. It is actually approaches to. If x is approaching to A, if x is very near to A, if the difference between x and A is very small, then the difference between f of x and L is also very small. F of x is also approaching to L. This situation is symbolized using this notation as limit extends to A, f of x is equals to L. There are different functions, different examples and many problems related to this notation and the definition of limit, and we will discuss all these things in the coming videos. So don't forget to subscribe and share the video.